All right, now it's recording again. All right. So when we talk about the electrical component of this process, within the cell, believe it or not, there is a voltage. And if you were to use, as electricians do, something called a voltmeter, you would compare the difference of voltage within the cell relative to outside of the cell. And within the cell, at rest, before any action potential or anything is going on, the cell membrane is roughly negative 70 millivolts. I say roughly because in reality, it does vary a little bit here and there. Sometimes it might be negative 72 millivolts, a little bit less. But in general, the average we estimate to be about negative 70 millivolts. Now, we rely on ions, and ions are electrically charged objects, right? Particles. And what we need to know is that the particles of interest are sodium and potassium. Now, there are others that are important, like calcium and so forth. But for this demo, this discussion, we'll talk about sodium and potassium. Does anyone know the charge of sodium? What is the abbreviation when you say sodium?
Na plus.
Right on. Good job, Shannon. Na plus. Why the plus?
Because it's a positively charged ion.
Right on. Good job, right? So it's a positively charged ion. So that's why it's abbreviated as Na plus. How about potassium?
Same. K plus.
Good job. K plus, right? So we have sodium and potassium, which are the two major players in the action potential. Sodium, generally speaking, has a higher concentration outside of the cell. Potassium has a higher concentration inside the cell. So what happens with an action potential? What we see is that in order for an action potential to occur, and an action potential is just a fancy way of saying the neuron firing, right? So in order for an action potential to occur, you have to have sodium enter the cell. Now, if your resting potential was negative 70 millivolts, right? And sodium enters the cell, what's going to happen? What's going to happen to the inside of the cell?
It's going to become more positive.
Or we'll start with less negative. We're saying the same thing, Shannon, though, right? It's going to become less negative, right? So think about this. Let's imagine this were a bank account. And for whatever reason, the holiday spending or whatever it might be, you went into overdraft. And you get an alert from, let's say, Chase Bank. Your bank account is negative $70, right? And then you put $10 in. What's going to happen to your bank account?
It becomes less negative.
It becomes less negative, right? So we'll start with that. So it will, your new bank account value would report negative $60, right? And the same thing can be said about positive ions entering the cell. You're starting at a negative 70 millivolts, but sodium is a positively charged ion, which is going to depolarize the cell, right? So it's going to make that neuron less negative than at resting potential. That's what depolarization is. Now, in order for an action potential to actually occur, it has to hit a threshold. Now, different books will say different thresholds. Some books will say negative 55 millivolts. Some books will say negative 50 millivolts. But the depolarization has to get to a certain point. And with an action potential, remember the following phrase. With an action potential, it's all or none. If you don't hit the threshold, you will not have an action potential. If you do hit that threshold, then you will certainly have an action potential. So you have to hit threshold for an action potential to occur. Now, when you hit that threshold, you're going to have a spike of neurological impulse temporarily. And we call that rising phase, or the first half of the action potential. We call that the absolute refractory period. And during the absolute refractory period, remember, sodium came in, it's temporarily going to be more positive, but it even goes above 0. And this is probably why Shannon said what she did, saying it becomes positive, right? Now, I said, hang on, it becomes less negative than rest, because we don't know if enough sodium came in to have an action potential. But if you do have an action potential, it's going to briefly become, the inside of the cell, it's going to briefly become positive. Now, the falling phase is referred to as the relative refractory period. We have what's called repolarization. Now, repolarization is the process of going back towards rest. And everything from the peak down to negative 70 millivolts is a repolarization process. However, similar to a person running downhill very fast, you can't stop immediately. We also have something called an overshoot, which is a hyperpolarization process where at the end of the action potential, before it goes back to rest, temporarily the neuron becomes hyperpolarized or more negative than rest. Now, the rising phase of the action potential is due to sodium. The falling phase is due to potassium. So here's how it works. Sodium enters the cell, depolarizes the cell. But I said potassium's on the inside. What do we know about magnets? Opposites attract. Like charges. What happens with like charges?
They get pushed away.
They repel. Opposites attract, like charges repel. And that was the reason why I asked you what the abbreviation for sodium and what the abbreviation for potassium was. Because you have Na plus entering a room, so to speak, full with K plus. So you have two positively charged ions trying to approach one another. So what happens? Temporarily, when sodium enters, potassium gets kicked out of the cell. It's like, no, we can't be here together. We're both positively charged ions. So potassium gets kicked out. And then ultimately we have what's called the sodium-potassium pump, which resets the system, which says, okay, we have sodium actually belongs outside of the cell. Potassium actually belongs inside the cell. So it says, all right, sodium, please leave. And it kicks it out. And then it says, potassium, please come back. And between action potentials, the sodium-potassium pump is responsible for resetting the whole system. Now I see there's something going on in the chat. Okay, fair enough. So here is another visual depiction of an action potential. As I said, your first phase, right, is resting potential, right? So we're at negative 70 millivolts. Then we have depolarization and our threshold. This point here is what happens when sodium enters the cell. If it hits the threshold, which we said was roughly negative 50 millivolts, you're going to have a spike where it actually temporarily becomes positive, as Shannon said, right? So this whole part up to the peak is the rising phase of the action potential. I said largely due to sodium. Potassium is on a delay, right? So potassium eventually has to be kicked out of the cell. So potassium leaves. And what does that do? Let's imagine we now have $50 in our account and we spend 20. Well, we're going to have less in our account. So when potassium leaves, you're going to repolarize the neuron and it's going to go back towards rest. And then I mentioned this overshoot, right? This hyperpolarization, right? So we have potassium wind up leaving, but it doesn't stop at rest. Temporarily, it's going to be slightly negative. That's what we call hyperpolarization. And then the sodium potassium pump resets the system to bring it back to rest. So in this picture, it describes all of the phases, right? Now, I mentioned that the two primary players are sodium and potassium. That doesn't mean there aren't others. For example, we have chloride, right? We have calcium, which are other ions that are responsible for neuron functioning. But primarily, sodium and potassium is at play here with the action potential. Are there any questions on the action potential?
I have a question.
Yes.
So what will happen if potassium and sodium stay in the same place?
They won't. It's a good question. But what happens is there are something called concentration gradients, which forces these electrical charges to push away from one another. So because they're both, try and put two poles of a magnet that are positive together. There's a force field that will naturally push them apart. Now, in a theoretical sense, let's say your question was true, that it did manage to stay. Well, you're going to increase the risk of a seizure. Think about that for a second. Why would you increase the risk of a seizure if you maintain too much sodium and too much potassium inside the cell? The answer is simple. You're going to have recurring action potentials, right? So the neuron's going to fire, 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 and seizures occur from excessive firing of neurons in the brain. So in principle, if that were to occur, you would run the risk of seizures. That would be the best practical answer. Now, I mentioned to you that the rising phase of the action potential we refer to as the absolute refractory period. Now, a refractory period is a period of time where a neuron that is firing cannot fire again. So once it's fired, there is a time it needs to reset. So the absolute refractory period is no, we're not going to fire no matter what. Absolutely, we're getting just the action potential we're working on. Now, but I use the falling phase I refer to as the relative refractory period. And that's interesting because during the falling phase, if more sodium enters the cell, you can have additional action potentials. So instead of the graph looking like this, watch my cursor. It goes up and then it keeps going up, 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 fire, 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 all the way up here until sodium stops going, and then it goes down the race. So during the falling phase or the relative refractory period, if you have subsequent depolarization, you can have trains of action potentials. And I appreciate the question because that reminded me to tell you that, right? So if you had too much sodium in the cell and it didn't leave, it's going to cause a train of action potentials. Does that answer your question?
Yeah.
Perfect. Good question. So that is the electrical element of the cell, right? So inside the cell, it operates based on electrical properties. In the next video, we're going to talk about the chemical properties, right? And how the chemical properties work.